We're going to get started with the first step in the completeness theorem proof. This step involves making a set that's infinitely large, and because it's so big, it's going to turn out that being a member of the set works just like being true on a truth assignment. So, okay, just a little bit of recap. The claim we're interested in proving is the completeness theorem, which says that if gamma truth functionally entails S, then gamma must allow us to derive S. In the last video, I talked about how we're actually going to be proving an alternative claim that has the completeness theorem as an immediate consequence. And we're just going to prove this alternative claim because it just turns out to be a little simpler to do so. So the claim that we're actually going to prove is if gamma is consistent in SD, then gamma is truth functionally consistent. In other words, to spell it out a little more clearly so that the definitions of consistency get fleshed out more, we're proving the claim that if you can't derive a contradiction from gamma in SD, then there's a truth assignment that makes every sentence in gamma true. Okay, so we're starting with this claim about a set of sentences of such that if you were to construct a derivation out of them in SD, you would not be able to derive a contradiction. So in that picture, truth assignments aren't really relevant yet, right? All we know is that you can't derive a contradiction from them in SD. And we want to take that set and prove that there is a truth assignment that makes all the sentences in that set from which it's impossible to derive a contradiction in SD true. All right, so that's the thing that we're proving. And how are we going to go about proving that? Well, here's our strategy. We're going to take gamma and make it bigger so it becomes easier to specify a truth assignment that makes every sentence in gamma true. Okay, so remember, that's our aim, right? We want to find a truth assignment that makes every member of gamma true. How we're going to do that is we're going to take gamma and make it bigger. Okay, so you might be wondering, how on earth is making gamma bigger going to make it easier to specify a truth assignment? Well, let me start out by providing a toy example to show how making a set bigger can actually make it easier to specify a truth assignment that makes every member of the set true. So consider the following set of sentences of SL: A or not B, if C then B, and not B or D. Okay, this is a set of sentences that's consistent in SD. So if you used these sentences as premises in a derivation, you would not be able to derive a contradiction from them. Okay, so now our goal is to find a truth assignment that makes every member of the set true. So to do that, we're going to expand the set. Specifically, we're going to expand the set so that the set contains every sentence letter in the set or its negation. All right, so to start out, I'm going to write out all the original members of the set. Okay, so now we want to expand the set so that the set contains every sentence letter or its negation. So we have 4 sentence letters, A, B, C, and D. And now we just have to think a bit to figure out whether we want to keep its sentence letter in there or have its negation such that the set remains consistent. Okay, so there are actually a ton of truth value assignments that are going to work for this set of sentences, and that's okay. We just want to find one truth value assignment that makes every member of the set true. So the fact that there are many alternatives doesn't really change our goal here. Okay, so now we ask, should we include A or should we put in not A? Well, A only appears here, right, in the disjunction, and let's just say A is true. Okay, so in that case, we're going to include A as a sentence letter. And now we're going to take B, right? So B appears in several places, but let's just think about it again in the first disjunction. So there not B appears. So whether B is included or not B is included doesn't matter yet because A is true, right? We made A true here. So the disjunction is already true. But let's just say that B is false. Okay, so in that case, we're going to put not B in the set. So if this is the case, then both disjuncts in that first disjunction are true, but the disjunction overall still comes out true, so that's fine. Okay, so now we move on to C. So C only appears in this material conditional. We know that not B is the case, right? So B must be false. So we can't have C be true, because if C were true, then the material conditional would be false, and that wouldn't give us a truth assignment on which every member of the set is true. So we need to make C false. Okay, so I'm going to put not C into the set. Last sentence letter is D. D only appears in this last disjunction. We already know that not B is the case, so we know that this side of the disjunction is true. So this side of the disjunction can be anything, right? But let's just make it so that it's also true. So the disjunction comes out as true, so we'll add D to the set. Okay, so now we have a set on which every sentence that contains the original set, but we made it bigger so that it also contains every sentence letter or its negation. I'm just going to clean this up. Whoops, that was a B. Clean it up a little bit. Okay, so now we have this bigger set that contains every sentence letter or its negation. And now, because we have every sentence letter or its negation, we can start to construct a truth assignment on which every sentence letter gets assigned true, and if the negation appears, then that sentence letter gets assigned false. So here's our truth assignment. A is true, B is false, C is false, and D is true. And this is a truth assignment on which every member of the original set is true. Okay, so that's how this method of expanding the set and making it bigger can actually help us get a truth assignment on which every member of the original set is true. That was a toy example where we knew exactly what the set we were working with had in it, but in reality, we know very little about gamma, right? The set that we want to make bigger, except that it's consistent in SD. So how are we going to make that set bigger? Well, how we're going to make gamma bigger is we're going to build an infinitely large set that's consistent in SD, gamma infinity. So it looks like gamma sub infinity. And we're going to make gamma infinity maximal consistent in SD. What it means for a set to be maximal consistent in SD is there are two components. First, the set must be consistent in SD. So it must be a set such that it's not possible to derive a contradiction from it in SD. And second, if you take any sentence that's not already a member of gamma infinity, sentence S that's not a member of gamma infinity, and add it to gamma infinity, the result is an inconsistent in SD set. So the thought here is in SD set. The thought here is that gamma is so big that if you take any sentence that is not already a member of gamma infinity and you add it to gamma infinity, the result would be a set that allows you to derive contradictions. So gamma cannot get any more consistent than it actually, gamma cannot get any bigger without becoming inconsistent. Okay, so that is our goal now. We want to build gamma infinity, this maximal consistent SD set, and the reason why we have to build this sort of set in the abstract, rather than as we did up here, where we built this like very concrete set, where you knew exactly what you had to add and you added the sentences one by one, is because we don't know enough about gamma in the proof we're doing. All we know is that it's consistent in SD. Right, so we have to build this set that's infinitely large to accommodate the fact that we don't know much about it. Okay, so we know that we want gamma infinity to be maximal consistent in SD, so now we're going to figure out how to build it. So to build gamma infinity, we need a way of numbering every possible sentence of SL so that we can keep track of whether to add it to gamma infinity or to keep it out of gamma infinity. So we need to assign every natural number a sentence of SL, and we need to assign, conversely, every sentence of SL with a natural number. So step 1 is to assign every natural number a sentence of SL, and every sentence of SL a natural number. So here's what that's going to look like. Let's have all the natural numbers here, blah, 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 up until n, all the way to like infinity. Okay, and so we want to assign each natural number a sentence of SL. So let's call that S1. So S1 is a sentence of SL that gets assigned to 1. And then S2 will be a sentence of SL that gets assigned to 2. S3 is going to be the sentence of SL that gets assigned to 3. And Sn will get assigned to n. Okay, and that goes on forever. So the thought here is that every natural number will get assigned a unique sentence of SL and vice versa. And the reason why we have to do this is because we have to keep track of every single sentence of SL to know whether we should add it to gamma infinity. Okay, so again, gamma infinity is going to be infinitely large, so there are infinitely many sentences of SL we have to consider. And given that sentences of SL can get really long, right, you can have infinitely many numbers of connectives in a sentence of SL, that makes sense. Okay, so now the question is, how do we figure out what specific sentence gets S1 or S2 or S3, right? What do those specific sentences look like? So here's the method we're going to use to figure out what each of those is. The first step is to assign every symbol in the language SL a number. So step 1, assign every symbol in the language a number. So what kinds of symbols are there in SL? Well, we have the sentence letters. So we have A, B, C, and D, all the way to Z. And we also have the logical connectives. So we have negation, and, or, if then, and if and only if. We also have the parentheses. Okay, I'm going to omit the square brackets because that's just another way of writing parentheses. Okay, and we also have numbers in case we have subscripts to any of our sentence letters. Okay, and then there are infinitely many numbers. So now we want to assign each of these a number. All right, so let's say A gets 1, B gets 2, C gets 3, and D gets 4. Okay, and then all the way to Z, which gets 26. Okay, and that completes our numbering of the sentence letters in SL. Okay, so let's say that the negation gets 27 because it's the next thing after all the sentence letters, and gets 28 or gets 29, if then gets 30, if and only if gets 31, open parentheses gets 32, and close parentheses gets 33. Okay, and then let's say 1 gets 34, then 35, then 36, then 37, all the way to infinity. All right, so that completes our first step of assigning every symbol in the language a number. So step 2 now is to assign every sentence a number based on how we've numbered them here. So we're going to this becomes kind of like a code that allows us to order the sentences of SL. So step 2 is to assign every sentence a number. So take the following sentence of SL. A or B and C. We'll actually have to have open and close brackets at the beginning and end for that to be a sentence of SL. Okay, so now we look at our code. And we see that open bracket gets 32. And here we have another open bracket, so 32 again. A gets 1, or gets 29, B gets 2, close bracket gets 33, and gets 28, C gets 3, and close bracket gets 33. This gives us a number, okay? So the number is 3232129233283333. A very long number, but this is basically the code we have for this sentence of SL. Notice that this is the only sentence of SL that gets assigned this number. It's a unique number, right? Because no other sentence of SL can have this particular ordering of symbols. So this is the only possible sentence of SL that can get assigned this number. Okay, so every sentence of SL gets a unique number. And now what we're going to do is we're going to order those numbers smallest to largest. So let me go back to purple, 3. So step 3 is to order the sentences from smallest to largest on the basis of the number that we assigned them. So order the sentences from smallest to largest. Here is what that's going to look like. So on one hand, we have the sentence of SL A, okay, and A, the code for A is just 1, right? Because if we look up here, A, the code for A was just 1, and that's the only sentence of SL that gets assigned 1. And that's also the smallest sentence of SL, right? So that's just going to be 1 in our ordering. Okay, so this is the code, right? That's the order, and this is the sentence. Okay, so that's done. Now let's go to the next sentence, which is going to be B. Okay, and then B, the code is 2, and its place in the order is also 2. So that's going to be really easy for the sentence letters, right? But eventually we're going to get to a place where there are certain codes that are going to be missing, right? So not every code is going to match up perfectly with its place in the ordering. And the example that we did above is one example of that. So we have the sentence A or B and C. The code is 3232129233283333. Its place in the ordering, however, might be something like 10,793. Okay, I have no idea what it is, but it's not the case that its code corresponds to the number that it is. All right. Okay, so that once you do this, though, for every sentence of SL, you have a way of having a specific order of sentences of SL such that every sentence of SL corresponds to a natural number, and every natural number gets assigned a unique sentence of SL. Okay, so that's how we go about having a really organized list of all the sentences of SL. And what that allows us to do is it allows us to keep track of whether every sentence is going to be added to gamma infinity. And that is the next step of the proof. Now it's time for the fun part. We're going to start building gamma infinity. Get pumped. Okay, so we're ready to build gamma infinity now, and we're going to do it in stages. So building gamma infinity in stages. Whoa, I don't know what happened to my infinity symbol there, but it's cool. Okay, so remember that gamma infinity is a superset of gamma, and all we know about gamma is that it's consistent in SD. We have no idea about what sentences are contained in gamma. So, okay, stage 0 of building gamma infinity is just going to be to let gamma sub 0, so gamma at stage 0, be gamma. Okay, and remember, all that we know about gamma is that it's consistent in SD. So at every subsequent stage, so let's say stage n, consider Sn, where Sn is the sentence up here, right? And n is the number, the natural number that places the sentence at the order in the sequence that it's in. So this is why it was so important to enumerate every single sentence of SL so that we can keep track and know which stage that sentence is going to become relevant. Okay, so we're at stage N now. We're asked to consider Sn, and we're going to let gamma n, so the set gamma at stage N, be either gamma n minus 1, so the set that gamma was at the previous stage, union Sn, if gamma union Sn is consistent in SD. So if we're considering Sn, right, we're thinking at this stage, should we add Sn to the set? And the answer is yes, we want to add Sn to gamma infinity only if adding it to the set would keep the set consistent. Otherwise, we don't want it in the set. Okay, so that's the crucial bit, right? We look at Sn, we consider every other sentence in the set. If adding Sn would keep the set consistent, add it. Otherwise, we're not going to add it. So gamma n is just going to be gamma n minus 1 if gamma union Sn would result in an inconsistent set in SD. Okay, so that's the crucial fact, right? If you go back to our toy example, that was exactly the reasoning we did, right? For each sentence letter, we thought, okay, am I going to add A or am I going to add not A, right? And we made that decision on the basis of whether adding A or not A would keep the set consistent or not. Okay, so that's exactly what we're doing here, but we're keeping it in the abstract because we don't know what sentences are in the gamma we're dealing with. Okay, so just to repeat one more time, at every stage N, we consider the corresponding sentence of SL to that stage number. And then we're going to take the gamma, we're going to ask, okay, what does gamma n look like at this stage? If adding Sn would keep the set consistent, then we add it, and that's what gamma n becomes. But if Sn would make the set inconsistent, then we keep it out. It doesn't get added to the set. So at each stage, gamma n is defined to be absolutely sure that it remains consistent in SD. That's really important, so I'm going to write it down. At each stage, gamma n is defined to be absolutely sure that it remains consistent in SD. So there can be no point in which gamma n is inconsistent in SD, right? Because we are using this very precise method where at each stage we're being absolutely sure that the resulting set is going to be consistent. And if adding some sentence to it would make it inconsistent, then we toss that sentence in the garbage. Okay, so now we go through infinitely many of these stages, right? Because there are infinitely many sentences of SL. So now we're ready to define gamma infinity. So we have all these sets of sentences of SL. So we have gamma 0, which is a subset of gamma 1, which is a subset of gamma 2, all the way to gamma n, which is going to be a subset of, gamma n plus 1. Okay, and we say that gamma infinity is the union of all the gamma n's. Right, so gamma infinity is just going to be the union of all these sets. In other words, here's another way we could say it. Gamma infinity is just going to be gamma 0 plus every sentence of SL that gets added to the set using this procedure we've defined. Right, so it's going to be gamma 0 plus every sentence of SL, where adding that sentence would result in a set that remains consistent. Okay, So now we have gamma infinity, right? So gamma infinity is defined as the union of all the gamma n's. So just to keep track, right, of where we're at. So here's what we know about gamma infinity. Gamma infinity is maximal consistent in SD, right? So it's consistent in SD, and it's such that if you were to take any sentence that isn't already a member of this set and add it to gamma infinity, the result will be an inconsistent set. So the thought is that we've considered every single sentence of SL that exists, and every single sentence that makes the set consistent is already in the set. So you can't make the set any bigger without it becoming inconsistent. Okay, and 2, we know that gamma infinity contains gamma. Okay, that's really important because we defined gamma infinity at stage 0 as just gamma, and then we kept on making the set bigger, but the set always remains consistent. Okay, so what was the point of making this huge set? Well, what we're going to show in the next video is that being a member of gamma infinity is just like being true on a truth assignment. And here's a little glimpse at what that means. So on a truth assignment, right, we say that, like, for instance, S1 and S2 is true on a truth assignment if and only if S1 is true on the truth assignment and S2 is true on a truth assignment. Okay, so that's just something we say about truth assignments, right? And we know that from just the truth table of the ampersand. Okay, so it's going to turn out that the pattern for being a member of gamma infinity looks just like this. So we say that S1 and S2 is a member of gamma infinity if and only if S1 is a member of gamma infinity and S2 is a member of gamma infinity. So notice how the pattern here matches exactly. So that's what I mean when I say that being a member of gamma infinity is just like being true on a truth assignment. It's going to turn out that this pattern holds for every single logical connective of SL. And we're going to call this the regularity lemma, where regularity is pointing to the fact that the pattern between being a member of gamma infinity and being true on a truth assignment are regular, right? So they match exactly. And we're going to prove in the next video that the regularity lemma is true.